Okay, so in last class, we were talking about finding or approximating the area under a curve. The curve that we used was y equals x squared, and we went from x equals 0 to x equals 1. We can do that with any curve. Before we get back to approximating and finding the areas under a curve, I need to teach you a little bit more notation. So this is again from section 4.2. We're going to talk about sigma notation. I'm going to use K rather than I. The letter that I use doesn't really matter, but I'll use K for now. So this symbol right here is the Greek letter sigma, capital sigma. Looks sort of like an E. And what we have written here, when you write the letter sigma, you have a letter, which could be any letter, as long as it's the same letter that's in the expression over here. This is like your starting point. So this is your starting value. And this is your ending value. So you have a starting value and an ending value. And this is the expression you're supposed to evaluate. And sigma implies sum. So sum adding things up. So K starts at 1. It goes all the way to 5. And we're going to add up K squared as K goes from 1 to 5. So the first number that we're going to square because K squared is 1. So 1 squared. This is 1 squared plus, because we're talking sums. After 1 comes 2. So it's 2 squared plus 3 squared. Why are we squaring every time? Because this says K squared plus 4 squared plus 5 squared. That's our last number. That's our ending value. We stop. So this is just shorthand notation for 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared. We could work that out. So this is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25. So 1 plus 4 is 5, plus 9 is 14, plus 16 is 30, plus 25 is 55, unless I made a mistake. And if I did, let me know. So when you use sigma notation, it's just shorthand notation for a sum. Let's do another one. How about the sum as K goes from 3 to 7 of, let's make it K cubed. So this time our starting value is 3. We go all the way to 7. We're going to have a bunch of plus signs because sigma always means sum. And this time the thing we're going to evaluate is K cubed. So we start at 3. So 3 cubed. We go to 4. 4 cubed. 5 cubed. 6 cubed. 7 cubed. And we stop. And we can work this out. 3 cubed is 27, 4 cubed is 64, 5 cubed is 125, 6 cubed is 216, 7 cubed is 343, and we could add that all up if we wanted. So is sigma notation, is it making sense? It's just a shorthand notation for a sum. Does that make sense? Awesome. Okay, so let's do a couple more practice problems. How about this? Sum as, and again, the letter that I use doesn't make sense. If I'd written I equals 1 and then a 5 and then I squared, I would have exactly the same expression. As long as whatever letter is here is the same as the letter that's there, we have the same expression. So let's see, how about the sum as, I'm going to still use K. Might as well get into a habit, but we could use anything. K goes from 1 to 4 of 2 to the power K. So let's make it K goes from 0 to 4. K goes from 0 to 4. Write that one out. You don't have to evaluate it. You can if you want. So this time, the first thing we plug in is 0, so it's 2 to the 0, then 2 to the 1, 2 squared, 2 cubed, 2 to the 4th. That's our stopping value, so stop. And again, if you want, you can work this out. Anything raised to 0 is a 1. Anything raised to 1 is itself. 2 squared is 4. 2 cubed is 8. 2 to the 4th is 16. If you add that all up, you get 31. Now, notice, just by sort of accident, every single expression we've evaluated so far has had 5 terms. 1, 2, 3, 4, 5. And then 3, 4, 5, 6, 7. There's 5 numbers there. And there's 5 numbers between 0 and 4. 0, 1, 2, 3, 4. So every single example I've evaluated so far has had 5 terms. That's just an accident. I just happen to choose those. Now, hopefully everybody feels comfortable expressing sigma notation sort of in a sum where we have lots of different numbers. Let's just do one more. How about the sum as K goes from 1 to 10 of K. This one doesn't have 5 terms. And feel free to use, an ellipsis if you want, if you don't want to write it all out. This one has more terms. Start at 1. We just write the number itself, not K to anything. It's just K. 1 plus 2 plus 3 plus all the way up to 10. Then stop. And if you add up all the numbers between 1 and 10, I think you get 55. Excuse me. Now we'd like to be able to go backwards too. We'd like to be able to express a sum written out in long form as an expression in sigma notation. Let's make sure we can do that too. Let's start with a pretty easy one. How about 4 squared plus 5 squared plus 6 squared plus 7 squared plus 8 squared. Write that in sigma notation.
I have a question.
Oh, yes, absolutely.
What is next to the 2 up there? Like the one next to yeah.
That's a K.
Okay. I was just making sure. I couldn't tell.
Yep. You always feel free to ask.
Okay. Thank you.
You're welcome. So that's why we change the numbers in the exponent, because that's the thing that's changing. It starts at 0 and it goes 1, 2, 3, 4. But the K is up here, which is why this is changing every time. But this stays the same. The 2 in the base stays the same. So go ahead and write this in sigma notation. And when you write things in sigma notation, there's always more than one way of doing it. But I think the easiest way to do this one, I'm going to use K again, but you can use any letter you want. I'm going to start, K goes from 4 to 8. That's my starting value and my ending value. And I'm going to evaluate K squared. And like I said, there's tons of different ways to do it. This is I think the obvious way of doing it. But if I had written something like K goes from 3 to 7, well, let me go from K goes from 1, 2, 3, 4, 5. K goes from 1 to 5. Let me start K goes from 1 to 5. And instead of taking K and squaring it, I'm going to take K plus 3 and square it. This and this are exactly the same, because the first thing you square is 1 plus 3. That's 4. You square 4. And then the next thing you would square would be 2 plus 3. That's 5. And then 3 plus 3, that's 6. 4 plus 3, that's 7. 5 plus 3 is 8. It's the same thing. Two ways of writing exactly the same thing. And once you write 2, you realize there's infinitely many of them. And they're all equally good. So let's do this one. How about natural log of 1 plus natural log of 2 plus natural log of 3 plus natural log of 4. I don't mean to insult your intelligence, but let's just do that one. The obvious way of doing this is going from K goes from 1 to 4, and then just take the natural log of K. And there are plenty of other ways of doing it, but that, I think, is probably the most obvious. And most obvious doesn't mean you have to do it that way. Is everybody okay with this so far? Let's do one that's a little bit harder. Now, it's not like I haven't taught you what you need to know to be able to do this. You can still do this. How about 1 plus 3 plus 5 plus 7 plus 9 plus 11 plus 13? So you might be going, wait a second, how do I do that? Because the numbers like go up by 2. But think it over. It's not like there's a piece of notation you don't know. You're going to use exactly the same kind of notation we used before. There's not a new place to put in skip by 2. Think about your expression. Of course, there's more than one way of doing this. I don't know what's the most obvious to you. For me, I'm just going to count up the number of terms. 1, 2, 3, 4, 5, 6, 7. So I'm going to go, k goes from 1 to 7. That's 7 terms. And the first thing that I want to add up is 1. The second thing I want to add up is 3. Their numbers are going up by 2. What I'm going to put over here is 2 times k minus 1. Let's just convince ourselves that that's right. So the first thing that we add up is 2 times 1 minus 1. That's 1. And the next thing I add up is 2 times 2 minus 1. That's 3. And then 2 times 3 minus 1 is 5. 2 times 4 minus 1 is 7, and so on. All the way up to 2 times 7 minus 1, which is 13. So it's not like there was a piece of notation that you didn't know. All you had to do was put in the appropriate expression. And as I said, there's more than one way of doing this. I could have just as easily gone, k goes from 0 to 6, 0, 1, 2, 3, 4, 5, 6. That's still 7 numbers. Instead of putting in 2k plus, the 2k minus 1, I could put in 2k plus 1. It's the same thing. 2 times 0 plus 1 is 1. 2 times 1 plus 1 is 3. 2 times 2 plus 1 is 5. And the last one would be 2 times 6 plus 1. That's 12 plus 1, or 13. Okay, so let's talk about some formulas for sums. That's actually the plural of the word formula. It's not really formulas, even though that's what I said before. If you want to write formulas, that's fine. But put an AE at the end. Sort of an archaic form, I guess. So let's start off with some fairly obvious ones. So n is some number. N could be 5, n could be 7, n could be 10. So if we start off, k goes from 1 all the way up to n, whatever n is, of the number 1. So if I add 1 to itself, this is 1 added to itself n times. 1 plus 1 plus 1, there's n of them. This k starts at 1 and goes 2, 3, 4, all the way up to n. If I add 1 to itself n times, this is not going to be mysterious. This, of course, adds up to n. That's not a mystery. Here's one that's a little bit harder. Let's say I go from 1 to n, and this time I add up k. So this is 1 plus 2 plus 3 plus all the way up to plus k. There's a story, nobody really knows if it's true, about the famous mathematician whose name was Gauss, who's considered one of perhaps the greatest mathematician we know of. When he was a 6-year-old schoolboy, to keep the class quiet, his teacher assigned the class the task of adding up the numbers from 1 to 100. And Gauss, I think, thought about it for just a few seconds and wrote out the answer, 5,050. And the question is, how did Gauss do that? There's a variety of ways he might have done it, but if you add these all the way up, you end up with n times n plus 1 all over 2. So let's just take a look for a second at that problem that Gauss was doing. One plus 2 plus 3 plus 4 plus all the way up to like 97, 98, 99, 100. So in this case, n is 100. So according to this formula, the sum of that should be 100 times 100 plus 1 all over 2. So that's 100 times 101 over 2. And it works out to 5,050 for that example over there. Here's one way you can see why that's true. Maybe it's already occurred to you. What do you get when you add 1 and 100?
$101.
101. And what do you get when you add 2 and 99?
$101.
101. Same with 3 and 98. Same with 4 and 97, and so on. So how many of these pairs are there in this particular example?
50.
There's 50 of them. So there's 50 pairs, and all the pairs add up to 101. 50 times 101 is 5,050. Pretty clever, huh? So, but we could just memorize this formula if we want. N times n plus 1 all over 2. How about this? The sum, so that's the sum of the first n numbers. Let's say the sum as k goes from 1 to n of 2k minus 1. This is the sum of the first n odd numbers. So 1 plus, 1 plus 3 plus 5 plus all the way up to 2k, 2n minus 1. So the sum of the first n odd numbers. I'm not going to tell you the formula. You're going to tell me what it is. This is a pretty sweet little idea. So 1 obviously equals 1. 1 plus 3, sum of the first two odd numbers is 4. 1 plus 3 plus 5, 4 plus 5 are 9. 1 plus 3 plus 5 plus 7 is 9. 1 plus 3 plus 5 is 9, plus 7 is 16. 1 plus 3 plus 5 plus 7 plus 9 is 25. Do you recognize these numbers over here? 1, 4, 9, 16, 25. What are they?
Perfect squares.
Yeah, they're perfect squares. This sum is nothing more than n squared. If you're wondering why that might be true, we'd like something convincing to explain to us why that's true. My favorite proof of this is well, I don't know who it's due to originally, but I know it by a mathematician named Littlefield. It's what's called a proof by picture. 1 plus 3 plus 5 plus 7, and so on. Is everybody convinced that if you add the first n odd numbers, you're always going to end up, it's always going to make a nice little square. I find that perfectly convincing. If a proof is supposed to be something that convinces everybody can understand, for me, this is a perfectly good proof. Okay, so one more. K goes from 1 to n, so the sum of the first n squares. So 1 squared plus 3 squared plus 5 squared plus, and so on, all the way up to n squared. This one's a little bit more complicated. It looks a little like this. This is n times n plus 1 times 2n, oops, 2n plus 1 all over 6. Sure, that was on the tip of your tongue. By the way, these numbers that you get when you add up the first n natural numbers like 1, 1 plus 2, 1 plus 2 plus 3, there's sometimes, well, let me just show you. 1 plus 2 plus 3 plus 4. So the fourth number, if I add up the numbers 1 plus 2 plus 3 plus 4, I get 10. It shouldn't be too surprising that these things are sometimes called the triangular numbers, just like these numbers are called the perfect squares. That should be obvious. They form a triangle. If you're wondering how to visualize numbers like 1 squared plus 3 squared plus 5 squared, oh, sorry. No. That's not what I meant to write at all. Not the sum of the squares of the first odd numbers. I want the sum of all the numbers. 1 squared plus 2 squared plus 3 squared. Sorry about that. The formula on the right-hand side is right. Oh, good thing I looked twice. So if you're wondering how to visualize this, if you're a sort of visual kind of person, think of each of these things as like a stack of oranges or cannonballs or something. So 1 squared, that's just one orange or cannonball, one sphere on the top. And it's sitting on top of like 4 oranges. Like you could imagine an orange and it's sitting on top of like a row of 1, 2, 3, 4 oranges in a square. And that square is sitting on top of like 9 oranges in a square, like 1, 2, 3, 1, 2, 3, 1, 2, 3. And so you have like this pyramid, like the way that pirates used to stack cannonballs, or at least in my mind on the ships, like this big pyramid of cannonballs. That's what you have here. I don't know how well it works for cannonballs. Probably works better for oranges. Okay, so sigma notation, we've got some formulas under our belt. Now we're going to go back to that problem of finding the area under a curve. In fact, I'm going to use exactly the same curve that we were using last time. Hopefully everybody has this. So remember what we did last time. We did several things, but one of the things we did is we estimated the area under the curve y equals x squared between x equals 0 and x equals 1 using n equals 4 equal subintervals and doing a right-hand sum. We did a left-hand sum too. But let's just focus on the right-hand sum for a second. You remember what we did. We had y equals x squared. It was a parabola. From x equals 0 to x equals 1, we want the area underneath this curve here. That's what we like. We weren't able to find it exactly, but we were able to approximate it. We took interval 0, 1, and we broke it up into, we were told, into 4 parts. So if we break 0, 1 up into 4 equal parts, we have a dividing line at 1/2. That breaks it up into 2 equal parts, and then 1/4 and 3/4. And we built rectangles which touch the curve. On the right-hand side, we were doing a right-hand sum, so these rectangles touch the curve at the right-hand side. This is all in your notes. And we computed the area of these 4 rectangles, length times width, and we added them all up. We can compute the area of rectangles easily. We knew how high each rectangle was because it touches the curve on the right-hand side. So all we had to do to get the height of that point is to figure out, you square the y-coordinate is always the square of the x-coordinate for this particular curve. And I think we worked out that the right-hand sum was what, 30 over, something like 15 over 32, I think. You can double check your notes. Whatever that works out to be. And we saw that this is definitely an overestimate of the true area under the curve, because not only do we have all the area under the curve, but we have this stuff that sticks over the top of the curve. So it's an overestimate. And I asked you near the end of the class, well, what happens if we break this up into more parts? Instead of 4 parts, what happens if we break it up into 10 parts or 50 parts or, or 100 parts? And you correctly answered that the more parts we break it up into, the more accurate our estimate of the area under the curve is. If I take the same curve, and I break it up into lots of parts, and I put rectangles on top of each one, these rectangles, if I do a right-hand sum, these rectangles still stick above the curve, but oops, too far. Okay, there we go. These rectangles still stick above the curve, but they don't stick above the curve nearly as much. And so we still have an overestimate, but it's it's much closer to the true value. And of course, the downside is that we have to do a lot more work. Okay, that upside, the downside should be relatively obvious. The upside is if we break it up into more parts, the bed is bigger, we get a more accurate answer. The downside is that we have to do much more work. So what I want to do is this same problem, but this time I'm not going to specify what n is. We're just going to leave it unspecified. So we're going to estimate the area under the curve y equals x squared between x equals 0 and x equals 1. Using n equals subintervals, so doing a right-hand sum using n equals subintervals. Now, I'm not going to specify what n is. I'm not going to tell you. So our answer is going to have an n in it. Okay, so let's draw ourselves a picture. Draw a little bit bigger. We're still going from 0 to 1. This is still y equals x squared. And I'm going to break it up into, I don't know how many parts, just n. So if we break the interval 0, 1 up into n parts, how wide is each part? We broke it up into 4 parts. Each part was 1/4 wide. If we broke it up into 10 parts, each part would be 1/10 wide. So if you break it up into n parts, each part, so each subinterval will be 1/10 unit wide. Oh, sorry, 1/n, not 1/10. Sorry, they sounded the same in my head. It came out my mouth wrong. So we break this up into n parts. I don't know how many parts it is. I'm going to leave it unspecified. So dot, dot, dot. The first dividing line is going to be at 1/n. And the second dividing line is going to be at 2/n. And the third dividing line is 3/n, 4/n, however many parts there are. So this is going to be 1, which is the same as n/n. And this is going to be n minus 1/n, n minus 2/n. That's probably getting too small to see. So 1/n, 2/n, 3/n, 4/n, however many parts there are, n could be 10 or 100 or 1,000 or 341. N minus 2/n, n minus 1/n, and n/n, which is the same as the number 1. Then we're going to draw rectangles. However many rectangles there are n of them. But I didn't tell you what n was. Just doing this generally. As I said, our answer is going to have an n in it. It's supposed to be a rectangle. That's a pretty wonky looking rectangle. But hopefully you know what I mean. And let's figure out the area of each of these rectangles. So we need the height of each of these rectangles. The first rectangle touches the curve on its right-hand side at 1/n. So its y coordinate is going to be the square of its x coordinate, 1/n squared. The second rectangle touches the curve at x equals 2/n. So its y coordinate is going to be 2 over n squared, 3 over n squared, 4 over n squared. The second last one is going to be, its x coordinate is n minus 1 over n. So its y coordinate is going to be n minus 1 over n squared. And this last one touches the curve at 1, in other words, n over n. And its y coordinate is going to be n over n all squared. So let's do that right-hand sum. Area of that first rectangle, length times width, or width times length. Its width is 1 over n, and its height is 1 over n squared. That second rectangle, its width is also 1 over n. All the rectangles have the same width. And its height is 2 over n squared. The third rectangle, its width is still 1 over n, and its height is 3 over n squared. I'm running out of room on the board, but presumably you have more room on your page. All the way up to the second last rectangle, n minus 1 over, still 1 over n wide, n minus 1 over n squared tall. And the very last rectangle, still width 1 over n, its height is n over n squared. So that's the height of, that's the area of all those rectangles added up. This is the area of rectangle 1. This is the area of rectangle 2, rectangle 3, however many there are, all the way up to the last one. And there are n of them. Let's just do some algebra. So let's square each of these out. So 1 over n. When you square a fraction, you just square the top and square the bottom. It's 1 squared over n squared. The second one, 1 over n, 2 squared over n squared. One over n, 3 squared over n squared. Plus dot, dot, dot. The second last one, 1 over n, n minus 1 squared over n squared. And the last one, 1 over n, n squared over n squared. A little bit of algebra, squaring the fraction by squaring the top and squaring the bottom. Let's keep going. So if I multiply the tops and the bottoms now, I end up with 1 squared from this first term on the top and n cubed on the bottom. 1 times 2 squared is just 2 squared, and n times n is n cubed. 3 squared over n cubed, dot, dot, dot. The second last one is going to be n minus 1 squared over n cubed. And the last one is going to be n squared over n cubed. And let's just factor out that 1 over n cubed we have in each one of these terms. And what we're left with is 1 squared plus 2 squared plus 3 squared all the way up to n squared. That should be looking familiar. I could write that out in sigma notation if I wanted to. I don't have to, but let me just go ahead and do that. 1 over n cubed. In sigma notation, that expression is the sum as k goes from 1 to n of k squared. Just says, if you don't like that, just leave it like this. If this is clearer to you than that, by all means, leave it like that. But we have a formula for the sum of the first n perfect squares. That was the last formula I gave you, I think formula number 4. We saw that it was n times n plus 1 times 2n plus 1 all over 6. And so this works out to n times n plus 1 times 2n plus 1. We multiply the tops. Oops. N times n plus 1 times 2n plus 1. If we multiply the bottoms, 6 times n cubed is just 6n cubed. Well, that's pretty darn impressive. If I plug in n equals 4, I'm going to get exactly the same answer that I got last time. N equals 4 equal parts, I'm going to get whatever it was, 15 over 32, once you reduce it. If I plugged in n equals 10, I would get the area of the rectangles if I had 10 rectangles. If I plugged in n equals 100, I'd get the total area of the rectangles if I had 100 rectangles. And we know that as n gets larger, the area under the rectangles, so the right-hand sum, gets closer and closer to the true value under the curve. We say the true area under the curve. In other words, the true area under the curve equals, and now we tie it back into calculus, the limit as n goes to infinity of this expression. That expression by itself is the total area of n rectangles. If we let that n go to infinity, we get the true area under the curve. You know how to evaluate this. We just multiply the top out. We end up with, let's see, n cubed, n plus 3n squared plus n over 6n cubed. That's something that you know how to do. We multiply the top and the bottom by the same thing. It's just like when we were doing horizontal asymptotes. That's exactly what we're doing here. Limit as n goes to infinity, 1 plus 3 over n plus 6 over n squared all over sorry, this should be 2n cubed, not n cubed. That should be a 2n cubed, so that's a 2. All over 6. And as n gets big, that goes to 0. That goes to 0. We're left with 2/6 or 1/3. The true area underneath the curve is 1/3. We needed calculus limits to get to the end point. Any questions? Well, thank you for your patience. I know I went a minute over time today. I will see you all on Wednesday.
Professor,
Yes.
I have a question for
Yes.
the class.
Yes.
A little bit of time.
Yep.
So for last week, I don't know if maybe it's different for me, but I don't have any like homework questions online.
So, yep. That was my fault. I got a little bit behind posting. They are posted now. Just go ahead and do them. I won't worry about the due date. Get them done basically before the end of the semester.
Okay, are the lectures posted as well?
The lectures are posted. The assignments are posted. So there's 2 assignments from last week rather than 3.
Okay.
But they are posted now, and I do apologize. I've been trying to keep up as well as I possibly could, but last week I got behind.
That's
But
no
everything
worries.
is posted now, and I think I can get today's up in a relatively timely fashion. But thank you for asking.
No worries.
Any other questions? Okay, I will see you all on Wednesday.
Thank you.
Thank you.
Thank you. Have a good
My
day.
pleasure.